Let's make sure some people don't fall out at the top of a loop. Alright, so we've got roller coaster of mass m, the yellow rectangle right there, going around a vertical circle with a radius r on a roller coaster track. Oh! We've got tangential velocity and a centripetal force. So this must be uniform circular motion. Remember, the lowest value the normal force can have at the top is 0. If normal force at the top becomes negative, the car falls off the track and the passengers fall out. Therefore, there's a minimum speed at the top. We've done this problem before. Yes, this is a different way to solve it. There is a minimum speed at the top that the car must go in order to not lose contact. At the top, normal and weight both point down towards the center of the circle, so both are considered positive in Newton's second law equation. So at the very top, we have the weight and we have the normal force of the track going down, and all of that will equal mv squared over r, our centripetal force. If the car's speed is v minimum at the top, then Fn is exactly 0. So mg equals mv squared over r. The mass cancels out and we can solve for speed, and we get v equals square root of g times r. I don't know if you remember, but that is the exact same process that we've looked at before. As a car travels up the loop slows down as kinetic energy becomes potential energy. That means the car has to go even faster than square root gr at the bottom when entering the loop. Let's use conservation of energy to find the minimum speed at the bottom to make sure we go all the way around the loop without falling off. At the bottom of the loop, the height and potential energy are 0. The speed is v, so there is some kinetic energy. At the top of the loop, the height is 2r, which is the diameter of the loop, and the speed is v equals square root gr. So there's both kinetic and potential energy at the top of the loop. If you were presented with this question, you would probably, or you wouldn't, but some of your classmates probably would freak out and completely forget what they know about a circle. And they would say, there's no height given. Just don't lose your mind. Remember, the height of this circle is just going to be the diameter of the circle. Alright, so looking at our kinetic energy and gravitational potential energies in our equation, we have at the bottom no gravitational potential energy, and at the top we have a nice, delicious mixture of the two. So we have mass canceling out again. Plugging in v at the top equals square root g times r, and migrate the 2 coefficient in the last term to the front. We get 1/2 v squared on the left side, and then we have 1/2 square root g times r squared plus g times 2r. Masses cancel out, and we substituted the velocity. Going further with our algebra, we're going to square that so our radical goes away. Multiply every term by 2 and combine like terms on the right side. Multiplying every term by 2 because of this 1/2. So we're going to multiply by 2 on each side. And when we do that, because we have 2 terms over here, we have to multiply by 2 to this, multiply 2 by this. And we get the speed at the bottom is the square root 5 times g times r. Alright, now if the roller coaster is released from a height h above the lowest point of the loop, what is the minimum value of h needed to go around the loop safely? What? We've already solved for the minimum speed that we need to enter the loop, right? So we already know what's happening down here. It's going to be kinetic energy only. And over here, it's going to be gravitational potential energy only. At the bottom of the loop, the minimum safe speed is square root 5 times g times r, and there is no height. So our equation becomes mgh equals 1/2 mv squared cancel m's in every term, plug in v at the bottom, which is over here, square root 5 times gr, and then we're squaring that, so the square root will go away, and we get h equals 2.5 times r. You should be able to do this. At this point, you've done conservation of energy a few times. You've dealt with circles before. We're just putting it all together, going deeper into the problems. So the release height must be half the radius higher than the highest point at the loop, if the loop is to be successfully completed. Here's a video of a guy who leaves a ramp on a skateboard, and the ramp is not half the height. Half of the loop's radius higher than the loop. Let's see what happens. So I keep getting hit with these YouTube copyright strikes. So I'm going to try playing this. If I get another strike, this may be the last video ever. But I think if I play it without sound, maybe. And it's a reaction video, so there's my cover. Ready? Let's see. Oops. Sorry. Oh, that was scary. He's alright. I'm sure he's good. But he's survived. If you look carefully again, you can see that that ramp is just not high enough.